What's up, everybody? Mr. Kozad back again with another video lesson. Thank you so much for finding this video, whether you are here because you have to be one of my students or you just found it randomly on the YouTube. I am so happy that you're here. I gotta tell you, today is a great day to be alive. I don't know where you are or what you're doing, but somebody's got to hear that. Today is a great day to be alive, and I'm so happy that we get to spend the next little bit of time together. So our topic for today is, this is an Algebra 2 lesson on conic sections, and we are going to be looking at ellipses, okay? Ellipses. All right, so all you need to know, if you're my student, this is section 9.4 in our textbook. All you need for this lesson is something to write with and something to write on, and we're ready to jump right in and have some fun. So here we go. Ellipses, here we come. Before we move on, real quick, it's ellipse, not eclipse. That was that weird movie about I think the werewolves and the vampires. I'm not really sure. I never saw it, but it's an ellipse, not an eclipse. Okay, save the vampires and the werewolves for the movies. Save the ellipses, ellipses for Algebra 2. Okay, so here we go. Let's jump in. First thing that we're going to do is we're going to spend some serious time unpacking, thinking about what an ellipse actually is, okay? Now, some of you were maybe taught that this shape was called an oval, okay? If I showed you the shape and asked you to identify it, some of you would say an oval. Well, the actual real mathematical term for a shape like this is an ellipse. It's an ellipse, okay? So make sure that you keep that in mind. The other thing that I'll tell you is that this picture, okay, or an ellipse can be oriented two different ways. We'll talk about that kind of in the next slide, but this is just one particular way. Notice how it's stretched out long this way, okay? Stretched out long this way, okay? It's also possible to be stretched out long this way, okay? I'll show you a couple different examples of that as we go, okay? All right, so let's unpack this picture here, this diagram, this basic shape, and identify some of the key attributes, okay? So, all right, first step is to identify the center, okay? The center of this ellipse will always have the coordinates HK, okay? Always have the centered at HK. Now, this is a little different because the center, HK, is not actually a point on the ellipse. The ellipse is this shape out here. So the center is obviously not on the ellipse. Think about it very similar as the center of a circle, okay? All right, so the next attribute that we're going to talk about is we're going to go out here on the far right and the far left. And these 2 points have special names. These points are called a vertex. Now, what's interesting about the word vertex, the plural of vertex, I'll write it down here, is vertices. So we would say that this particular shape has 2 vertices. Not one vertex, but 2 vertices. Again, that is plural for vertex. Okay? Next attribute, excuse me, that we'll see is these points in the opposite direction from the center. Okay? This is called a covertex. A covertex. So obviously, if you had to guess the plural of covertex, it would be covertices. Covertices, okay? I like to think about this as every pilot has a co-pilot, and every vertex has a covertex. Notice that the distance between the center and the covertex will always, always, always be shorter than the distance from the center to a vertex. The distance from center to vertex is always greater than the distance from the center to a covertex, okay? Next points that we see here, let's keep going with the points, are these points, okay, right here and right here. Those are called focus points. Those are called focus points. We talked about a focus point when we talked about parabolas a few lessons ago, okay? And if you think about it, this is actually, if you think about this one half as a parabola, you can see that the focus is on the inside. And if we think about this other half as a parabola, the focus is located exactly where you would expect it to be. But since the shape is kind of like 2 parabolas that are kind of glued together, there are 2 focus points. Now, this is kind of a fun word to say as well. We don't say focuses, okay? We say foci. The plural of focus is foci. Some people say foci. Some people say foci. Foci is a little safer for me to say. Foci, you got to be really, really careful that you enunciate that correctly because you don't want somebody to get the wrong idea, okay? Foci is much, much easier to say, but you'll hear some people say it different ways, okay? So there's actually just two more attributes that we need to identify. The next attribute is this line segment that connects vertex to vertex. Let me draw that again. The line segment that connects vertex to vertex, it has a name. It's called the major axis. It's called the major axis because that is actually the longest line that you can draw in this ellipse, okay? Now, some of you are probably really, really wise, and you could already kind of guess what the line segment that connects the co-vertices is called. It's not the co-major axis. It's called the minor axis because it is smaller than the major axis, okay? Now, before we move on to the next slide, there are going to be some units that we're going to add to this that aren't going to make a ton of sense right now. But I promise you that after we do the next slide, we talk about some of these attributes, and we actually do some problems, this is going to make a lot more sense. So pay close attention here and add this to your graph or your picture here, your diagram. Okay, let's start with the distance from the, how do we want to do this here? Let's go from the distance from the vertex to the center. The distance from the vertex to the center of that graph is going to be A units, the letter A. A is a variable, and I'm about to teach you how to find that. Okay? Now, let's move on. The distance between the center and a co-vertex, the distance between the center and a co-vertex is going to be B units. Again, I will teach you how to find that. And then lastly, the distance from the, let me move HK down here. Yeah. The distance between the center and a focus point will be C units. C units. Now, just as you look at this picture, okay, you can probably already see that A will always be larger than B. A will also always be larger than C, okay? B and C, there aren't always rules on which one's larger. It can depend on the specific type of ellipse that we have. But please know that A is always going to be larger, okay? A is always going to be larger than B and C, okay? All right, so keep this labeled diagram of an ellipse handy. And again, before we move on, do me a favor, and I can't really do this because it's not, I don't think it's going to work. Actually, it might work. Let me try this. Let me rotate this page 90 degrees. Oh, yes, it worked. Okay, so what you can actually see is this is what a ellipse would look like if it was oriented the other direction. Notice how all of the labels, all the attributes are still the same. It's just instead of that major axis, the long axis, going left to right, it actually goes up or down. Okay, it goes up or down. So let me rotate that back, and I just do the, nope, oh, I'm not going the direction I want it to go. So let's rotate this counterclockwise. There we go, we're back. All right, so two different orientations. You've got this one, and you've got the one I just showed you where the major axis is vertical. Okay, all right. We're going to go through and we're going to write out some formulas here that's going to help us identify all the key attributes of these ellipses. So what I would do is pause the video now, and I would recreate this chart that you see in your notebook so that you can go through this pretty quickly as I do it with you. So pause the video now, make this chart, and then hit play again when you're done with that. Okay, welcome back. Hopefully you actually have a beautiful chart ready to go because we've got a lot of cool stuff to talk about here, okay? First thing that I want you to look at is look at the format of the equations that we're going to have. Look at the format. They are very, very similar. There's some subtle things that are different. See if you can, remember those little games where you had to like look at the two pictures and figure out what was the same and more importantly, like what was different? Can you find the major difference between these two equations? Look very closely. You're right. Hopefully you answered this out loud and it says, okay, what's changed here is the first numerator. X minus h squared is first in the first one, and y minus k squared is first in the second one. That's an important change. Instead of necessarily being first, what you want to look at is which one is with a squared. X is with a squared on the first one, and y is with a squared on the second one. I promise you that's going to make a lot more sense here in just a little bit, okay? Another thing I want you to notice here is that both variables are squared, very similar to a circle where both x and y are both being squared. The subtle difference here is that a squared and b squared will be different numbers. They will not be the same. Okay, so let's go through this. When x comes with a squared, okay, when x comes with a squared, and let's talk about a squared and b squared. I should have done that a minute ago, okay? Please remember that a squared is always going to be larger than b squared. Always. It's always going to be larger than b squared, okay? So if you go back and you look at your picture, remember a is the distance from the center to a vertex, b is the distance from a center to a covertex. So very clearly, a is always going to be bigger than b, always. So when you're looking at an equation, it's really simple. The way you identify which number is a squared and which number is b squared is you identify which one of these two values is the largest. You're looking for which one is the largest. When you find the larger of the two numbers, that is a squared. Once you identify a squared, then you look in the numerator and see what variable is in that numerator, okay? So in this case, x is with the numerator. Now, when x is with a squared, remember a squared is the larger of the two numbers. When x is with a squared, that orientation is called horizontal. That orientation is called horizontal. And what that means that the major axis is going to be horizontal. So this is like an ellipse that we just drew the diagram of. Oh, that's an ugly ellipse, okay? A horizontal ellipse is one that's kind of rotated on its side, if you will. It's longer along the horizontal, okay? All right, now some of you super type A personality types, you're gonna have a panic attack about this because I'm not gonna do this column in order. I'm going to go a little out of order. It's okay. Take a deep breath. Relax. Remember, life's too short to be stressed out all the time, okay? All right, so let's talk a little bit about the vertices. Let's do the vertices first, okay? Now, please remember that the center, let's add another note up here. The center for both of these scenarios is always going to be at the point HK. Always. It's always going to be located at HK. Now, on the vertices, think back or look back on the diagram that you just labeled, okay? And tell me what letter, A, B, or C, did we use to go from the center to one of the vertices? Okay? Hopefully you saw that letter is A. Okay, so think for a minute. If we're moving to the right A units and we're also moving to the left A units, here's how we're going to write our vertices. We're going to take our H value and we're going to do two things. We're going to add and we're going to subtract A, and we're going to keep the K value the same. So remember that each ellipse is going to have two vertices. That's why I get the coordinates by, number one, adding A to the H value, and then subtracting A from the H value. Okay? Same concept for the covertices. Go back and look at the diagram. What letter did we use for covertices? Okay? That letter was B. So on a horizontal ellipse like we have here, okay, we're going to go up B or down B units to get to the covertices. So that means we keep our X value the same, but we are going to add and subtract whatever B is to the K value or the Y value of our center, okay? Now next, the foci, okay, the foci. The only letter we haven't used yet is C, okay? The only letter we haven't used yet is C. So remember that the foci are always going to be on the same line as the vertices. So they're always going to be formatted very similar to the vertices. But instead of using A, we use C. Now, how in the world do we find C? How in the world do we find C? Well, there's a relationship between A, B, and C that you should always remember for an ellipse. And here's that relationship. C squared equals A squared minus B squared. Oh, wait, Cozad, you messed up. Haha, caught you. It should be a squared plus b squared equals c squared. That's Pythagorean theorem. I've learned that before. No, it's not. Okay, that is Pythagorean theorem, but we're not using Pythagorean theorem here, okay? We're using an application of it, which ends up getting us to c squared equals a squared minus b squared. That's not a mistake. You're going to need to remember that for an ellipse, that c squared equals a squared minus b squared, okay? So that's going to come in handy when we start doing some examples here in a minute, okay? Length of the major axis is 2a units. If you go a one way and a the other way, that's 2a. And then the length of the minor axis is 2b, or not to be. Sorry, I had to make it, that joke. It's bad, I know. That is the question. Never mind. Okay, stop, Cosad. It's not the time for dumb jokes. All right, so at any rate, so major axis 2a, minor axis 2b, or not to be. Okay, moving on. So if remember we said, okay, Cosette, how do we find a squared and b squared? Okay, we're going to look at these two numbers and you're going to figure out which one's larger. Okay, so we clearly see that a squared is going to be larger than b squared. And then we look in that numerator and we see, oh, y is with the larger of the two denominators. So when that happens, we have what's called a vertical ellipse. We have a vertical ellipse, so its orientation is vertical. And vertical ellipses look like this. They sort of look like an egg, okay? All right, so again, we're going to go a little out of order. I'm sorry if that makes you uncomfortable, but we're going to do it. So the vertices, let's start with those. So if we have a vertical ellipse, we start at the center, HK, and we go up A, and we go down A units. So to write that out, we keep the x value the same, and we add and subtract A to our K value. The covertices are going to go left and right for a vertical ellipse, so we're going to take our H value, and we're going to add and subtract B, and we're going to keep the Y value the same. Remember that the foci will always be formatted just like the vertices. They're on the same line. So our coordinates for our foci will be H, and then we have K plus or minus C. The length of the major axis is still 2a. That doesn't change. And the length of the minor axis is still 2b. Okay? So this is a lot of information, I know, and sometimes people try to just like memorize this chart and they're like, oh my gosh, that's so much to remember. It's really not. If you remember what A tells you, what B tells you, what C tells you, and how to find those three, you are going to be set. Okay? So let's actually practice these in the context of some examples. Okay? So here we go. Example number 1. It says sketch a graph and identify. I'm trying to see. Identify doesn't look like I spelled it right. Identify. I think it's right. All the critical attributes. Okay. So here we go. We're jumping right in. Okay. It's going to be awesome. So first thing that you do is you look and see, is the equation formatted correctly? Are both x and y squared? Yes. Does it equal 1? Yes. So we know there's not a lot of extra work that we need to do to get the formatting right. Okay. So now the next thing we do is we look at the denominators and we identify which one is larger. So you tell me, what's larger between 48 and 20? Hopefully you said 48. If you didn't, go take a nap. You're tired, okay? Get some sleep. So if a squared is 48, that means the other denominator is going to be 20, okay? So let's go ahead and find c squared as well. Now remember back from that previous slide, our relationship. C squared equals a squared minus b squared. So you're going to take the difference. A squared minus b squared gets me 28, okay? Now, what we need to do is take this one step further and take the square root of each one of these, okay? So the square root of 48, 48 is not a perfect square, but we can simplify that to 4 root 3. The square root of 20 simplifies to 2 root 5. And the square root of 28 simplifies to 2 root 7, okay? 2 root 7. So the next thing that we want to do is maybe draw a rough sketch of what this graph's going to look like. Okay, now remember on the last page I told you that you find the larger of the two denominators and then you look and see which variable's in the top. That variable is x. So what that means is we're going to have a horizontal ellipse that looks something like this, okay? Now, having the picture is going to help you remember what to do here. So let's identify the center, okay? The center is at HK. H is -2, K is 1. The center is at -2, 1, okay? Now let's find the location of the vertices. So what I'm going to do here is I'm going to take the center and I'm going to move to the right A units and to the left A units. So the way I'm going to write that is I'm going to do -2 plus or minus 4√3, comma 1. And that's going to be the coordinates of my two vertices. I go right 4√3 units and left 4√3 units. You can actually leave it formatted like this because it's not a whole number. Okay, so this is actually the most precise way to represent those coordinates. Co-vertices, we use the B value and we go the opposite direction. So we're going to add and subtract 2√5 from the Y value, okay, because we're going to go up and we're going to go down. And then to find the foci, we take the X value, -2, and we add and subtract the C value to get the location of my foci. Okay? The only other thing that we need here would be the length of the major axis, which is A times 2. So that would just be 8√3. And the minor axis is B times 2, which is 4√5. 4√5. So we sketched a rough sketch of the graph, and we've identified all the key attributes. Now, when I grade this, and when your teacher grades your work on this graph, what we're really going to be looking for is, are the attributes correct, okay, which you have down here, and mainly, is the orientation correct? Did you draw a horizontal ellipse? Okay, it's really, really important to identify that. All right, pretty easy once we kind of see how it all fits together. So let's move on to example 2. It says sketch a graph and identify all the critical attributes. Exact same directions. But, my people, is the formatting correct? No, it's not. Guess what time it is? Hasas time. If you are like scratching your head and like, this man's lost his mind and it's only 8:46 on Tuesday, May 5th. Hey, Cinco de Mayo, 8:46, let's go. You're thinking, this man has lost his mind. Okay, what's he talking about? If you don't know what Hasas is, you're probably not one of my students, and you need to go find my video on completing the square. It's where I teach my method of completing the square using an acronym Hasas, half, square, add, subtract. Now, this is so much fun, guys. I got to tell you, you don't get to Hasas just one time. No, that would be too boring, okay? Too beneath us. But my people, we get to Hasas twice, okay? You're probably applauding or just yelling where you are right now, just out of joy. You're welcome. You know, you can thank me later. Okay, so let's have some fun with this. Let's nerd out on some algebra. Okay, so 4x squared minus 32x plus y squared minus 4y equals -52. I'm just getting this set up to be able to do Hasas 2 different times, okay? So I moved the constant to the other side, grouped the x's together, grouped the y's together, so that we can do this. Now, remember, this is this is so fun. Okay, so on this, the Hasas for the x's, remember that we have to factor out that 4. So factor out the 4, so we get x squared minus 32 divided by 4 is 8x. Now, leave yourself a space because we're going to complete the square. So, Hasas says half, square, add, subtract. Half the middle number, which is 4, square it, which is 16, add 16 to create your perfect square trinomial, and then subtract. Now, a lot of you are real smart. You know we're not just subtracting 16, because everything in this parenthesis is being multiplied by 4. So what we're actually subtracting is 4 times 16. Okay? So now let's do Hasas with the second set for y. Okay, this one we don't have to factor anything out. So we have 4, which is 2. 2 squared is 4. We add that. and then we subtract that. Now here we can actually just subtract 4 because we're not multiplying by anything in the front, okay? So that still equals negative 52, okay? Now let's clean some things up. So we have 4 times x minus 4, the quantity squared, plus y minus 2, the quantity squared, equals, let's add 48 and add 4 to the other side. No, 16 times 4 is not 48. 16 times 4 is 64. So 64 plus 4 added to the other side, I think that gets us 16. It should get us 16. Okay? Now be really careful here. You're not actually done yet, because remember that you want this equation to equal 1. So what we're going to do is we're going to divide everything that you see here by 16. Divide everything you see by 16. So what we end up getting is we get x minus 4 squared. 4 over 16 simplifies to 4, plus y minus 2 squared over 16 equals 1. And this, my people, is the equation that we are going to use. Okay? Now, obviously, I have run out of room, so what I'm going to do is I'm going to take this beautiful work that I just did, and no, I'm not going to erase it. I'm just going to make it a little bit smaller. I'm going to let it shrink. Keep you up there. Let's take this. Let's move you up here. And now let's jump right in. Okay, look at your denominators. I've got a 4 and a 16. What's larger? 16. So then look at the top and see what variable comes with 16, and that's y. So that tells you that this ellipse is going to be a vertical ellipse, something like this. Okay? So we're going to find our center, and we're going to find our a value, b value, and c value. Okay, so let's do a, b, and c first. So a squared we know is 16. B squared we know is 4. C squared is the difference between those, so we get 12. Now I like where these numbers are going. A is 4, B is 2, C is 2 root 3. Okay? Now let's go through and let's label our attributes here. Okay, the center. The center we find using H and K, so that's 4, 2. The vertices. Remember, we always use the A value for the vertices, and we're going to go up A, and we're going to go down A, because this is a vertical ellipse. So we're going to keep the 4 the same, but we're going to add 4, go up 4, from 2, so that's going to be 4, 6, and there's also going to be a vertex at 4, negative 2. Okay? My co-vertices, I'm going to go left and right by b units. Okay? So that's going to be 2, 2, and 6, 2 are the location of my co-vertices, because I'm going from the center, and I'm going right 2, I'm going left 2. And then to find the foci, I'm going to go up C and down C. So I'm going to keep the 4, and I'm going to take the y value, and I'm going to add and subtract 2 root 3. Now, Cosette, how come on the vertices and the co-vertices you split those into 2 points, but on the foci you left it as a combination like this? Well, if you know A and B were whole numbers that were easy to write out the coordinates, I can't do that here because 2 root 3 is irrational. It's going to be a pretty ugly decimal. So I'm just going to leave it like this. This is the most descriptive way to leave that. Okay? Awesome. Major axis is 8. Minor axis is 4. We don't need to take time on that. That's pretty easy. Okay? Moving on. Number 3. Number 3. It says write the equation of an ellipse that has vertices at -1, 11 and -1, 1. And co-vertices at -4, 6 and 2, 6. Now, I love questions like this. They're actually way easier than the other ones, in my opinion, okay? So whenever you're asked to go the opposite direction, you're asked to write the equation, you're going to work backwards, okay? So let's graph or draw a rough sketch of the information that they've given us. Okay, they say that one vertex is at -1, 11. Let's call that point -1, 11. And another vertex is at -1, 1. Now, right away, that tells me that this is going to be a vertical ellipse, because I know that the vertices are on a vertical line, so that's going to tell me that it has to be a vertical ellipse. So right now I already know that I'm going to have an equation y minus k squared over a squared plus x minus h squared over b squared equals 1. Okay? Now what we also know, we know the center is going to be halfway between those 2 points. So find the midpoint of -1, 11 and -1, 1. Okay? They're 10 units apart. Divide 10 by 2, you get 5. So come down 5 from -1, 11, and you end up at -1, 6. So there's our center. So now let's take this equation one step further. So that's going to be y minus 6 squared all over a squared plus x plus 1 squared all over b squared. That equals 1. So now, to be done, I just have to figure out what a is and what b is. Well, we just talked about that. A is the distance from the center to the vertex, and we got that as 5. Okay? So what we can actually do is we can replace that a squared with 25. Okay? So now we just have to figure out what b is. And we'll use b, we'll find b using the information given about the co-vertices. It tells us that one co-vertex is at 2, 6, and the other is at -4, 6. Well, simply count how far the center is to one of the co-vertices, and you get that b equals 3. I don't want to erase that. You get that b equals 3. So when we plug that in, we get y minus 6, the quantity squared, over 25, plus x plus 1 squared over 9 equals 1. And that, ladies and gentlemen, is an equation that has those characteristics. Okay? All right, y'all, we've got just one more problem to do. Thanks for sticking with me. I know this is a long one, but I appreciate you sticking around, okay? Write the equation of an ellipse that has a major axis that is 10 units in length, okay, and a co-vertex at 4, -6 and 0, -6. All right, so number one, the major axis being 10 units tells me that A is 5. Remember that the major axis is 2A, so we know that this is that the A value has to be 5. So let's draw a picture of where the co-vertices are located. Okay, so we've got one at 0, -6, be like right here maybe, and one at 4, -6. Okay, now remember, those are the co-vertices. Okay, so if the co-vertices are left and right, that means that the vertices are going to be up and down. So that means that this is actually going to be a vertical ellipse again. Okay, it's going to be a vertical ellipse again. So let's find our A value. We already said is 5. And our B value is the distance from the center to one of those co-vertices. So let's find the center point. The center is halfway between the co-vertices. So the point that's halfway between there would be 2, -6. Again, we know that A is 5. So we count the total distance of the minor axis is 4 units. Cut that in half, we get 2 and 2. So that tells us that the B value is 2. Put it all together. Y plus 6 squared over 25 plus x minus 2 squared all over 4 equals 1. Final answer. Whew, that's a long one. That is a long one, but that is a fun one. You can thank me later. You guys are the best for sticking around. There's probably only 2 of you that made it this far. If you're one of the lucky 2 that made it this far, man, would you drop a comment on this video, and I'll send you a very, very special Cozad joke just for you to enjoy. Thank you so much for sticking around. You guys are the absolute best. I hope this was helpful, and I will see you next time.